Hi there. This video is an exam paper walkthrough of the Eduqas GCSE Mathematics Higher Tier Component 2 paper from autumn 2022. This paper is worth 120 marks in total, and this is the fifth video of 6. It will focus on questions 17 to 20, which account for 22 of these marks. Eduqas Component 2 papers are calculator papers, so a calculator should be used. A little disclaimer, there may be more than one way to answer a question. The methods shown in this video are not the only way some mathematical skills can be applied. Okay, let's get started. Question 17. So we've got a cuboid and it says the diagram is not drawn to scale, so we can't measure anything directly from it. The diagram shows a cuboid A, B, C, D, E, F, G, H. So this is our cuboid here. Calculate the length of the diagonal F. So we're trying to calculate the length of this diagonal here. So this is 3D Pythagoras, guys, okay? So this takes some visualizing, but bear with me. So what I can do here is if I join the diagonal DB, and then I'm going to highlight in orange this triangle. So FB hits the floor horizontally with DB, so that's flat on the floor. So this forms a right angle here, guys. So I have a right angle triangle, this being the longest side because it's opposite the right angle. I have the side 72, so if I find this side here, I can use Pythagoras to find DF, okay? What I've also got formed down at the bottom here on the base of the cuboid is another right angle triangle. So this is where you need to be able to picture these things. So that cuboid is flat on the floor, guys. So that means that this is also a right angle here. So I'm going to use this smaller green triangle to find the length DB using Pythagoras, and then once I have the length DB, I'm going to use the bigger triangle to find the length DF. So DB is equal to the square root of 33 squared plus 56 squared, okay? So the square root of 33 squared plus 56 squared, which is 65 centimetres. So DB is 65 centimetres. So now I'm going to find DF. So DF using Pythagoras should be equal to the square root of these two sides squared added together. So 65 squared plus 72 squared is 97 centimetres. And that's our answer for DF. 18a, the diagram shows a sketch of the graph y equals f of x. So this is y equals f of x. Point A has coordinates -3, 0. Point B has coordinates -1, 1. Part 1, sketch the graph of y equals f of -x on the axes below. You must indicate coordinates of the new positions of point A and B. Okay, so the -x means we're changing the sign. It's inside the bracket, so it's the x coordinates that are changing. So because the x coordinates are changing, it's going to flip the graph over the y-axis. So this is actually a reflection in the y-axis. So for point A, the x-coordinate is -3, the y-coordinate is 0. The y-coordinate is not changing, but the x-coordinate, we're going to change the sign. So instead of it being -3, point A is going to be at +3. The y value staying the same, guys. Let's look at point B. So remember, the x value changes sign, the y value stays as it is. So as the x value is -1, it's going to become +1. So let's put that here. So x is +1, the y value stays the same, and then we just need to draw the graph reflected as best we can. It doesn't have to be perfect, just has to be as similar as possible with the correct new coordinates labelled. Part 2, sketch the graph of y equals f of x plus 2 on the axes below. You must indicate the coordinates of the new positions of the point A and B. So we're starting with this original graph again, but this time the change is happening to the y coordinates because it's outside of that bracket. So what's happening is we're adding 2 to the y coordinate. So it's going to shift everything up 2 places, sorry. So here the coordinate of A is -3, 0. X is going to stay at -3, but that 0 is going to move up 2. So A is going to go from here, it's going to go up 2 places. So A is -3, 2. B, the X coordinate is staying the same, but the Y coordinate we're adding 2 to. So when we add 2, it's going to go up by 2 places. So the Y coordinate becomes 1 plus 2, which is 3. But the X coordinate stays at -1. So X coordinate is at -1. So this is 2. So let's call that 3. So B is -1, 3. Don't forget the origin here. It's currently at 0, 0. But everything's shifting up 2 places. So the origin is going to move up to 0, 2. There. So we're going to draw that in as best as we can with those points labelled. And you can see then that this graph, everything has shifted up 2 places. Part B, the diagram shows the sketch of the circle with equation x squared plus y squared equals 289. Write down the coordinates of point C. So the equation of a circle is in the form x squared plus y squared equals the radius squared. C is on the circumference, so from the origin to C, that is the radius. So if r squared is equal to 289, then r, the radius, must be the square root of 289. So it equals 17. We want the coordinate of point C. So the x coordinate is 17, but the y coordinate is 0. So we're going to put 17, 0 as our coordinate. Question 19. So we've got a diagram here, not drawn to scale, so we can't measure anything directly from it. In the triangle ABC, so ABC, AB equals 7 centimetres, AC equals 9 centimetres, and the angle ABC equals 61 degrees. So ABC, 61 degrees. Find the angle BCD. So BCD. So this is the angle that we're looking for here, guys. Okay. So we're currently dealing with a non-right angle triangle. And we need to find this angle here. So what would be really helpful is if we knew this angle, because then these are angles on a straight line, and then we could calculate the angle that we're looking for. So we're looking for this one here, X. So what we're going to do here is we're going to use a sine rule to find this angle, because we have an angle on opposite side, an angle on opposite side in a non-right angle triangle. So when we're using the sine rule to find an angle, we flip it upside down. So sine of the angle BCA, we'll call it, the angle here, over 7 is equal to sine 61 over the opposite side, 9. So sine of the angle BCA is equal to 7 multiplied by sine 61 over 9. But we want the angle BCA, so we're going to do the inverse sine of this whole thing here. And I'm going to put it in my calculator. Just put that there to remind us it's an angle. Exactly as you can see there. So we have the inverse sine, so shift and sine, and then it's 7 multiplied, and then everything else is in a fraction. So it's sine 61, close the bracket, over 9, arrow off the fraction, complete the bracket. So that angle is 42.8639459. So BCA, that's this angle here. So we're going to subtract that now from 180 to find the angle that we're missing. So angle BCD is 180, subtract angle BCA. I'm writing it like that so I don't have to write this out, but I've kept it on my calculator to make life easier. So 180, subtract that answer, is 137.1360541. They haven't asked me to round it in any way, so I'm just going to leave it like that. So the angle BCD is 137.1360541 degrees. Question 20. So we have a diagram here, not drawn to scale, so we can't measure anything directly from it. The diagram shows a sector of a circle with centre 0 and radius 12. So this whole shape here is the sector. Angle AOB is 55 degrees. AOB, 55 degrees. Find the area of the shaded region. Okay, so to find the area of the shaded region, we need the area of the full sector, and then we need to take away the area of this triangle here. Okay, so let's do the area of the sector to start off with. So we do the angle we're given, theta over 360, because sector is a part of a circle and there are 360 degrees in a circle, and then we multiply that by the formula for the area of a circle. So let's substitute in what we know. Theta is the angle that we've got enclosed within that sector. So that's 55 over 360 multiplied by pi, multiplied by our radius squared, which is 12. It's also shown on the diagram there. So 12 squared. So let's put that in our calculator exactly as we can see it there. 55 over 360 multiplied by pi, multiplied by 12 squared. So that gives us 22 pi centimetre squared. So that's the area of the sector. Now we need to deal with the area of the triangle. Okay, so when we're working with the area of a triangle that's not a clear triangle that has a base and a height that we can multiply and divide by 2, we're using the trigonometric formula for area, so the sine rule for area. So area of the triangle, so this rule is a half AB sin C. So we're doing a half multiplied by AB, which are the radii that enclose this angle here. So remember, this is also a radius, so it's 12 centimetres. So it's a half 12 times 12 times sin of the angle that we're given. So that's 55. So I'm going to pop that in my calculator. So a half 12 times 12 times sin 55. So that's 58.97894719. So the area of the shaded region is the area of the full shape, the sector, subtract the triangle. So shaded region is 22 pi subtract this. I've kept that long decimal in there, so 22 pi subtract my answer is 10.1360919 centimetres squared. Again, they don't ask me to round it in any way, so I'm not going to. I'm just going to leave it like that. Part B, find the perimeter of the shaded region. Okay, so we want to find the perimeter of this shape here, guys. So we need to know this length, and then we need to know the arc length, and we need to add them together. So let's deal with the arc length first. So arc length. So the formula for the arc length of a sector is, again, the angle that we're given divided by 360, but this time multiplied by the formula for circumference, so pi times diameter. The angle inside is 55, so that's 55 over 360 multiplied by pi. Now the radius is 12. If the radius is 12, the diameter is double that, so that's 24. So multiplied by 24. So let's stick that in our calculator. 55 over 360 multiplied by pi multiplied by 24. So 11 over 3 pi. I'm just going to leave that in exact form for now. So that's the arc length. I now need to find the length AB. So I'm going to have to work with this triangle, and I've got two sides in the enclosed angle, so I'm going to use the cosine rule to find AB. So AB squared is equal to the two side lengths squared. So 12 squared plus 12 squared, subtract 2 times those side lengths. So 2 times 12 times 12 times cos of the angle, and the angle is 55. So what I'm going to do to start off with is just simplify this a little bit so I have less to add into my calculator. So 12 squared plus 12 squared is 288. 2 times 12 times 12 is 288 cos 55. So this is what I'm going to stick in my calculator. So AB squared equals 288 subtract 288 cos 55. So that is 122.8099863. This is AB squared. I don't want AB squared, I just want AB. So I'm going to square root that answer. So we're going to square root this whole thing. So AB equals, now I didn't delete it off my calculator, so just square root of your answer. So that's 11.08196672. Doesn't say about rounding or anything yet, so that's also good. But we want the total perimeter, so we want the length AB plus the arc length. So we're going to do AB, so we're going to do AB plus the arc length of 11 over 3 pi, and I've put P there for perimeter. AB is still in my calculator, so I'm going to add the 11 over 3 pi to it, which gives me 22.60113978. Everything's in centimetres, so that's my perimeter in centimetres. Again, it doesn't tell me to round it, guys, so I'm not going to take the time to do that.